close all the shades all the time. It's light anywhere we want.
The dungeons.
So here we are. All right. Very good. All right, we'll get started. So a few announcements. So the first problem set is available on the web, and it's due in 1 week. Okay. We'll have a problem session tomorrow in this room at 2 o'clock. So yeah.
Doesn't matter which TA we go to.
I'll get that straight with them.
Okay.
Yeah, I'll get that straight with them before it's due. All right. The other thing is, there's a little when to meet poll, so fill it out so that you can see when there is availability to meet the team. Okay, so please do fill that out. Very good. The first video for this course was a bad experiment. A non-experiment was clearly because there was no solid angle for the camera to see anything. So you get to enjoy an audio podcast, but we fixed that. All right. All right. So let's just do a quick. Where are we at? So we're here to study quantum optics, and quantum optics, as I define it broadly, is the study of quantum coherence in and by light, okay? So it's the study of the light itself and the quantum nature of the light, in particular what we call quantum coherence in light. And by light, I mean this in the broadest term, electromagnetic wave. I mean, interestingly, when people typically in the early days thought about, well, when do we have to worry about quantum effects in the field? It's at high energy, right? I mean, you usually think about high energy physics is when I really need to worry about the quantum effects in the field. Well, that's because for massive particles, I need to be at high energy to be relativistic, but photons are relativistic no matter what energy they're at. And so you always have quantum effects in electromagnetic fields at any energy scales, including in the microwave. These days, at a gigahertz, centimeter long wavelength, that's a pretty low energy photon. We can still, nowadays, especially in modern quantum computers and superconducting circuits, we're manipulating the quantum coherence in microwaves. So that's something that people would never believe that is important, okay? But it is. Okay, so coherence, by coherence, what I mean by that is coherence is the ability of a system to exhibit interference, okay? So we're familiar with interference as a wave phenomenon. In classical physics, we have interference of waves, and in particular of interest right now are the interference of electromagnetic waves, okay? So the intensity of the electromagnetic wave, a typical detector that detects electromagnetic energy is what we call a square law detector. It typically depends on the square of the field because it depends on the intensity of the field, okay? And the intensity is proportional to, and we won't worry about the constant out front, to the square of the electric field and the time average. Typically, the detectors don't respond to the instantaneous field, but to its time average. And when we have a monochromatic field, which we can represent as the real part of some complex amplitude, then it's the square of the complex amplitude that is the intensity, okay? All right, so as in particular, if we have a situation where our field is a superposition of the electric fields arising from two sources, and the electromagnetic field Maxwell's equations are linear, so when we have one solution and another, the sum of them is also the solution. And we look at the intensity associated with this, then the intensity of this field is not just the sum of the intensities associated with these two fields. But in addition has an interference term. This cross term is the interference term, okay? And so we're looking at a way in which we observe such interference, and this kind of device, an interferometer, this particular kind of interferometer is known as a Mach-Zehnder interferometer. Kind of hard to align compared to a Michelson, but it's easier to draw compared to a Michelson interferometer. So we often just draw this. We'll talk a lot more about this as a device that an interferometer is the device by which we make the most precise measurements in the world by looking at this kind of interference. And so in this interferometer, we have this kind of two paths that the light beam can take. It could take path A or path B, and then we might be looking at a detector at each output port. Which has some intensity that it's measuring. Okay? And so the question is, how do these intensities at these two output ports depend on the parameters that define the interferometer? Okay? So in particular, this interferometer has different optical components. It has a beam splitter. No guess, that's a beam splitter. And then we got mirrors. So the question is, in classical optics, how is the amplitude transformed as we move through this interferometer? Okay, so when this beam splitter passes, the field passes through this beam splitter, it partially transmits. Its amplitude and its phase are affected. And because it's both its amplitude and its phase are affected, we encode that in a complex number, which is the transmission amplitude, okay? So that's a complex number. Or the field might be reflected, and upon reflection, the amplitude and phase are affected, and the way that's encoded is through the reflection amplitude. So these are complex numbers because we're talking typically, always when we do this, we're thinking about the response at a particular frequency. I mean, generally these will depend on the frequency of the field, the transmission and reflection coefficients, but we're fixing that at the moment, okay? And so we can think about a linear transformation of the two modes, that's what we call them, we'll talk about the term mode a little bit more, that transforms. This is really a scattering process. This is wave scattering. So the waves come in and the waves go out. And the scattering matrix is this matrix. I could call it the S matrix. It really is the same thing. For the case that this is a symmetric beam splitter, that is to say, if I flip it over, it's the same. It doesn't matter whether I'm coming in from port 1 or port 2, then it has this form. Okay, otherwise I would have to have indices depending on whether I come in this way. If I had a coded mirror, it would, of course, not be symmetric. But I'm just assuming it would be so for ease right at the moment. And so my transmission and reflection coefficients, as I said, they're complex numbers which have an amplitude and a phase, and by convention we typically call the square of this capital T and the square of this, the magnitude squared, capital R, which represent the fraction of the intensity and the fraction of that is transmitted and the fraction of the intensity that is reflected, right? The little t is the amplitude. And so if this is a lossless beam splitter, then the norm is conserved of this vector, which is to say that the total intensity in, the sum of the intensities here and here, must be equal to the sum of the intensities here and here. And so this matrix being unitary gave us certain conditions on these coefficients. So for example, well, what it means is that, you know, the total intensity is conserved. T, capital T plus capital R must equal 1, but also there's a phase relationship. So the reflection and transmission, the phases induced on the field upon transmission and upon reflection are not independent of one another. So in order for this to be a unitary matrix. And so what we have is that the phase difference must be some odd multiple of 90 degrees, or also known as pi over 2. And so, but what this doesn't determine is the overall phase, but if I'm for a square law detector, I don't care about the overall phase. So typically, we just choose that any way I like. So I could choose, for example, choose the phase upon reflection to be, upon transmission to be 0, no phase, and then the phase upon reflection to be pi over 2. If I add something here, it wouldn't change anything in terms of the intensity, because the intensity doesn't see the overall phase. It's kind of like why the wave function, we don't care about the overall phase of the wave function, because we only measure the probabilities, okay? All right, so, so for example, we might have a 50-50 beam splitter, which is to say T and R are 50%, capital T and capital R. So I could say T is the square root of 1 over the square root of 2, and R is I over the square root of 2. That's an example of a 50-50 symmetric beam splitter, where this matrix in that case would be 1 over root 2, 1, 1, I. That is the scattering matrix associated with the 50-50 beam splitter. That's symmetric. Okay. One thing to note about this particular matrix, and for this particular choice, no matter what I choose here, the determinant of U in this case, which is what?
1.
Is 1.
Right, yeah. So it's S.
And it will always be 1 in this case when I choose it to be a unitary, and I set the phase, and I forgot about the overall phase. This is a special unitary matrix. It's special because its determinant is 1, and 2x2 matrices that are unitary and special are known as SU2 matrices. We'll talk a lot more about SU2. SU2 is the group of 2x2 unitary matrices that have determinant 1. So I didn't have to choose the determinant 1, but by convention we typically do because we don't care about the overall phase. Okay? All right, so let's take a look again at our friend, oh, it's up there, the interferometer. And let's let's just calculate for this case, what is the intensity that comes out, say, port 2, okay? So the intensity that comes out port 2 in my Mach-Zehnder interferometer is the square of the complex amplitude associated with the electric field at that output port. Okay. Again, when I say equals, there's some overall constant. If I wanted to make this in watts per centimeter squared, I'd need some mu naughts or C's or whatever, but we don't worry about that one here. Okay. So what is that in relation to the input? So right now, the input field is only coming in port 1. I could have another input field in port 2, but for the moment, I put nothing there, okay? And I want to know what comes out port 2. So I need to calculate this. Well, I mean, what we see is there are two ways that, there are two paths that the field can get in order to get to this output port, right? So I have this possibility, where the field goes here. That's path A. But there's a superposition of that with, oops, it could be reflected from this and then be reflected from that guy. That's another path that the electric field can take. So the wave comes in, the wave is divided. Some of the wave propagates along path A and could then be transmitted, and some of the wave is reflected from the beam splitter, and this is path B, and so we'll call this the electric field that's out, that's due to path B. But the total electric field is the superposition of these, okay? So that tells me I can just write this down. So in path A, what do I have? Well, I take the initial input and it gets multiplied by first the transmission amplitude, then it's propagating and picks up a propagation phase because you get a phase upon propagation, which is e to the I omega over c times LA. There's also another phase that's picked up upon reflection at the mirror. So I get a -1. Okay, so that's the electric field associated with path A that comes out port 2. And then I have to add to that the electric field associated with this, the wave that went along this path. Okay, which is, it's the same input, but that input gets multiplied now by the reflection amplitude. It picks up a propagation phase associated with the path length that it went. This guy gets reflected again, and then there's also another -1 because there's a mirror over here. And upon reflection of the mirror, yes, Dave?
Should there be a reflection coefficient for E out to A? Because it also gets reflected by a mirror?
So there's two kinds of reflection coefficients. There's a reflection coefficient associated with the mirror, and there's a reflection coefficient associated with the beam splitter. Okay, so the reflection coefficient associated with the mirror is -1. Yeah.
You're missing a T there before -1.
I'm missing a T here. Yes, that's what I'm missing. Thank you.
No,
Yeah.
I think you already put that in. E1 and T.
There's two. No,
Oh, there's
because
two.
it transmits
Oh,
through
okay.
the first guy and then again.
Okay.
There are two transmissions. This one has two reflections. That is correct. Thanks. Thanks, Jane. So this is E2 out B. Okay? So let's take the case that we have this choice of the 50-50 beam splitter that's symmetric like this. So then this will be T times T is 1/2, and R times R is what? -1/2, because it's I over root 2 times I over root 2. And so what I get in this case is minus E in times 1/2 times e to the I C L plus e to the I over C. Let me just call that K. LB. Okay? So that's this. And so let's calculate the intensity. Okay? The intensity is the square of the amplitude. And the square of the amplitude will be the square of this plus the square of that, which is 1/4 I in, that's the square of this. The square of this is also 1/4 I in port 1. Right? And then I have the cross term, which is twice the real part of this times this, okay? Which is minus, so it's minus 2, because the minus sign is that, the real part of E in 1 squared over this times this 4 e to the I p L A minus L B. Okay? Which again is, so what this is equal to is this plus this is a half of I in plus this term, which is minus a half I in the cosine of k times delta L, where delta L is the path length difference. Yes, sir?
L minus, LA minus LB? Is that
Yes.
what it is? Okay.
Because it's this times this complex conjugate. That's where that came from. Everyone see that? Good. So, so what we find here thus is that this intensity is the incident intensity coming in port 1 times 1 minus cos k delta L over 2. Okay. Or I in 1 sine squared k delta L over 2 if you know something about trig identities.
It's so funny how with zero path difference, there's no chance.
Okay, so yes, and so let's write that down. So what we have thus is that the output intensity out port 2 is equal to the input intensity coming in port 1 times sine squared k delta L over 2. And the output intensity on 1, if we did the same calculation, well, it's a lossless beam, it's a lossless interferometer, so it's whatever the input intensity, the total input intensity, which is in port 1, minus the output intensity in port 2. Because the total intensity in 1 and 2 output must be equal to the total intensity input. Right? Everyone clear on that? And there's only intensity coming in one port, in this case, port 1. So this is equal to 1 minus sine squared is cosine squared. Okay? So what we see, as Ben was noticing, is if I look at the intensity at these caliper ports as a function of k delta L, I get this kind of interference pattern, or interference fringes, if you like, where this is I1 out, and this is I2 out. This is the path, this is 0, this is pi, this is 2 pi, etc. Let's take a close look at this and understand what's going on. Okay? When the interferometer is balanced such that the path length difference is exactly 0, no intensity at all comes out this port. All of the intensity comes out this port, because I1 out equals I in. I'm sorry, I1 out equals I1 in when the path length is 0. All of it comes out port 1. On the other hand, nothing comes out of this. If I have this at pi over 2, I have an equal amount of intensity. Half of the intensity comes out port 1, and half of the intensity goes to port 2. And then if it's a pi phase difference, all of the intensity goes out port 2, and none of the intensity goes out port 1. That is wave interference. That is, we have constructive and destructive interference.
Quick question.
Yes?
So we were looking at the field and the intensity, and
Yeah.
I get that, but it sounds like a big important thing here is the phase that we're dealing with. And my
Yeah.
understanding is the phase also shifts with the reflection and the transmission, and you've accounted for that in the RNT, correct?
All correct.
Okay, so here's then where I kind of break down. You say we don't care about the final phase, but there's always gonna
The overall phase doesn't matter, but the phase difference matters.
okay, but what about final phase? Is that overall phase? So what's the phase coming out of like E1 out? How do I relate that?
So let's just say, so the output intensity in port 2 was equal to the magnitude squared of the amplitude of the electric field that came out port 2 squared.
Yes. And the phase
This doesn't clearly, if I wrote this as a complex number with the magnitude and the phase,
would have to be.
it doesn't care about that overall phase, right? Because the magnitude of a complex number, which is, this is a different R, this is like, polar notation for,
Yeah.
complex numbers, this just depends on R. It doesn't depend on the overall phase. However, if I had Z1 plus Z2 is Z, and I look at the magnitude of Z squared, that's the magnitude of Z1 squared plus the magnitude of Z2 squared, plus twice the real part of Z1 complex conjugate Z2, which depends on the relative phase between Z1 and Z2, even though, so I could factor out an overall phase, but the relative phase of these two complex numbers is important. It's critical to whether this adds to 0 or not. This is what constructive and destructive interference are. Thank you for your question. It's important to clarify these things. Good. All right. So that's wave interference. It's classical waves. Okay. So, but oh. We need to know about Gaussians too. So, all right. So, this is. We would say that these waves, the waves exhibit temporal coherence. Because really what I'm looking at when I have something like a Mach-Zehnder interferometer is I'm looking at what the field was at two different times in the past, right? Because what I see here depends on what the field was doing at the retarded time. So this is what's called a temporal coherence. Okay. But what I want to talk about now is quantum coherence. What do we mean by quantum coherence? Well, quantum coherence is about interference of the wave function. So we're talking up to this point in today's lecture about the electromagnetic wave. The electromagnetic wave we think about as a physical entity equal and good to waves on a pond. It's relative to some oscillation of a physical field, okay? But the wave function is a little different. Nonetheless, there's important connections here. And over time, we'll unify these things together. So what is the wave function? The wave function is a probability amplitude. So instead of a field amplitude, I have a probability amplitude where the square of the amplitude is telling me something about the probability of an event happening, okay? So let's just do the only kind of experiment I can do, a Gedanken experiment, okay? You know what a Gedanken experiment is, it's a thought experiment. So here is my Gedanken single, or it's my single photon source. We don't really need this to be true to explain this, but I'll just start here, okay? So what do I mean by a single photon source? What I mean is a source where in every fixed time interval, there's exactly one photon. That's a very non-classical source of light. Laser light isn't like that at all. We'll come back to that, but that's another story, okay? Let's just imagine, because I really like to imagine, we have such a source, okay? And so I'm gonna put this on the 50-50 beam splitter. And so I'm gonna have two detectors at the output port, okay? What's gonna happen? So when this was a classical wave, and this was a 50-50 beam splitter, we would get, if there was a certain intensity in, half the intensity would come out here and half the intensity would come here. So we would get some photocurrent. In fact, we'd get equal photocurrent on both of these detectors. Half of the wave intensity would go here, and half of the wave intensity would go here, right? What happens in this case? Yes?
Half the SPD clicks is on one, half the SPD clicks
So-
is on the other.
Sometimes this goes click 50% of the time, and this guy goes click, makes that exact noise 50% of the time. But if I were to put a coincidence box here that says, when do these both go click within this time interval? And so if I timed it so that I never looking at two different photons, but one photon, I would never see coincidence. These two things wouldn't go click at the same time. Either this one would go click or this one would click, but never both. Okay? And which one goes click is completely random. It's completely random. And in my mind, this is the only and important problem in quantum mechanics. We have thrown cause and effect out the window. We have effects that have no causes. Now, you might say, Deutsch, give it up. That's life. You know, you gotta live, you might want a certain world, but that's not just the way the world is. And I'm fine with that. I'm fine with, I have to adjust to the world the way the world is. But what bothers me is I don't know when in physics I have to give up cause and effect and when I don't. You say it's when a measurement happens, but what the heck is a measurement? And there lies in the problem. Okay, we'll just leave that for food for thought. All right, so fine, that's interesting, but let's suppose now I take this single photon source and I put it into the Mach-Zehnder interferometer. Okay, so I have the Mach-Zehnder interferometer with these mirrors and 50-50 beam splitters and the two detectors at the two output ports. Okay, what's going to happen in that case? Yeah.
They have to click at the same time.
Only one detector will get clicks.
Only one detector quiz, and which one? Let's say it's balanced interferometer.
The one.
Also, the one on the right.
Is it this guy or this guy? Or both? Or randomly?
Random, it would have to be random.
No, I think that's
First
right.
interesting.
Right.
I think that's good logic. It would have to be random, right? Let's come back to that
No, we're
point.
measuring.
But it's not. 100% of the time, this one goes click, and 0% of the time, that one goes click. In exactly the same way that when I had the balanced interferometer, 100% of the intensity went out port 1, and 0% of the intensity went out port 2. In exactly the same way, if the interferometer is balanced, 100% of the time this detector will go click, and 0% of the time, unless they have dark counts, but we don't, go click over there, okay? And that makes no sense, okay? Because let's just think about this from the point of view of logic, okay? So we can say that there were two possible things that could have happened to this photon, okay? What makes this a photon is that it's indivisible. It's one photon under Einstein with liberty and quantum mechanics for all, okay? And so this photon can do different things. And I always take issue when people say the photon is in two places at the same time. No, the photon is in one place or another, but you'll never find the photon in two places at the same time. We'll come back to that story. So what happens? Well, there's a possibility that the photon goes on path A. Here it is. Photon goes through the beam splitter, bounces off the mirror, and then transmits again, and goes over here. Okay? That's a possible history. Okay? That will say that could give a detection over here is that the photon transmitted, reflected, and transmitted again. There's another history that that could have happened. Reflected. Mirror reflects me again.
The sounds of physics.
My life is a musical. So, and then it gets reflected again. So these are two histories that could have led to a click, okay? But what Feynman taught us, or the way Feynman expressed it, is that we must add the probability amplitudes for processes or histories that are indistinguishable. What we mean by indistinguishable is that there's nothing in the universe that can tell me which of these histories happen. All I know is I got a click here. And that could have happened this way, or it could have happened this way. These are the two different histories that might have led to a click. But I don't know. There's nothing in the universe that has a record of which path the photon took. And when that's the case, we have to add the amplitudes. Yeah, Donald.
Is that behind the one colloquium from spring, what is it, amazing Mandel effect or something like that?
Yeah, we'll talk about it. Yeah, we'll mention that in just a moment. Yes, sir.
Yeah. When we think of photon indistinguishability, that's something that's always kind of bothered me. Is it enough for me to think of it like it's just spatially? Should I be considered of things like the phase of the photon?
Well, I mean, we'll come to this in very much detail, but the real question is there any other degree of freedom of anything in the universe that is correlated with one of these histories or the other, that has a record that if I looked at that other thing, it would say, oh yeah, the photon went there. And it doesn't, it could be in the spatial mode, it could be in polarization, it could be in an electron, anything else. Yeah.
To clarify, what's indistinguishable here isn't the photons, it's the path the photons took.
That's right. I mean, what's indistinguishable is there's no record of anywhere of which path. The paths are indistinguishable. The processes are indistinguishable. Okay.
That doesn't matter. You just consider that it got there somehow.
Yeah, and if if there is nothing in the universe that could have told me, then they're indistinguishable. That's by definition. But let's just think about this before we go to our dear friend Richard Feynman. Let's think about, logically, we would just say, okay, if this were just, if we would use logic, the is by the theory of probability, the classical theory of probability, okay? So we would say the probability to see a click at output port 2 is, well, it could have taken path 1, or path A, and there's the probability of seeing it at 2 given that it was at A, okay? So if it took path A, there's some probability that it would get to output 2, or maybe it took B, and there's a probability. This is just the theory of conditional probability. That's logic. Everyone agree with that? So there's a choice. Either it went in path A, if it went, there's some chance it did, and if there's a chance it would get to 2. What's the probability of this photon going on path A? 50%. This is a 50-50 beam splitter. And the probability of getting to output port 2, given that it did this, is what? It's a half. Or maybe it went through B. The probability of B is that it got reflected at the first beam splitter. That happens with probability a half. And the probability to see it in here, which would have to reflect, that's another half, which would be this. So logically, the answer is random. It should go here or here. If you thought about classical logic, then there's no way in hell this should be 0. It makes no sense. Hence, quantum logic, right? Quantum logic would say we don't add the probabilities, we add the probability amplitudes, right? So the probability of coming out port 2 would be, there would be a square of an amplitude. And when we square this, we'll get these terms plus interference. And the interference terms are what can either reduce or enhance the probability of a given outcome through constructive or destructive interference of the amplitudes, okay? And that's what we call the fact that these two processes can exist in superposition with one another is what we call quantum coherence. So we can think about, let's just think about this interferometer again, and let's imagine that this difference is pi over 2. Okay? What happens in that case? Given the picture up here. 50-50.
Yeah.
Sometimes you'll get a click here, sometimes you get a click here, and it's a coin toss. You don't know which one. And so over time, if we collected many clicks, we'd find on average half of the clicks went here and half of the clicks went here, which is to say half of the intensity goes here and half of the intensity goes here, which is what we see when we have a power 2 difference. So what we observe as classical photocurrent, we can think about as a collection of discrete processes where there's a photoelectron that happens, but randomly here or here, but there's gonna be fluctuations. On average, we get the classical result, but there's also gonna be quantum fluctuations on top of that, because it doesn't happen exactly half, right? There are fluctuations around. What we call shot noise, we'll talk about more a little bit later. But the point I want to emphasize here is we can think about, and that's where we start to get our head wrapped around this notion of the electric field is like a wave function of the photon, is that the square of the electric field is kind of telling us something about the probability of detecting a photon in one place or another. The fraction of the light is like the probability. So the fact that there's a 50% fraction of the intensity that comes out the two ports when I have power 2 is to say that there's a 50% probability of a photon coming here versus here. Very good. All right, let me remind myself what I was going to say next. Oh yeah, I remember now. So there's this intimate connection here that we're seeing the relationship between classical wave interference and the interference of probability amplitudes in quantum mechanics. This particular kind of interferometer, which is only looking at the intensity in one port or the other, is what we call one photon interference, okay? It's one photon interference is that we see this interference pattern building up photon by photon, and importantly, it's related to the histories of individual photons, one photon. This one photon can go here, or this one photon can go there. It's one photon, we don't know which one it did. We add the probability amplitudes with those three histories, but it's one photon. And then we do the experiment over and over and over again, 10 to the gajillion times, and then we'll collect statistics. But it's a one photon effect, okay? That's a kind of what we'll call, so there's an interrelation. We saw this, the same interference we see photon by photon we see in the classical waves, okay? So this one photon interference is what we call classical interference. Because it's the same kind of interference we see in classical waves. But here's something different, you ready? Let's say I have a source that spits out pairs of photons, not just my single photon, but it puts out pairs of photons, and it puts in such a way that I can't tell which photon is which. These are identical photons, okay? And I'm going to take these two photons, they come out, and I'm going to reflect them and put them on a beam splitter. And now I'm going to have two detectors. Now it's not one or the other, they both could go click. And in particular, I'm going to look at coincidence counts. So I want to look for situations where both of these detectors go click. In which case, I get a photo kind of gates and it goes click when I get two photoelectrons at the same time. So this is a coincidence counter. What are the processes that can lead to that?
But to get two on one detector?
I could get both, so there's four possible processes that could happen. Either this photon and this photon both go through, that's transmitted. They both get transmitted at the beam splitter. Or this one is reflected and this one's transmitted. That is, say, TR. then they would both come out over here and I'd see no coincidence. Or I could have this situation where this guy gets transmitted, this guy gets reflected. That's the amplitude associated reflected times transmission. Or
Both are reflected.
they both are reflected. So now I ask you, which of these processes contribute to a coincidence count?
Both
I
transmitted, both
think transmitted.
Either they're both transmitted or they're both reflected. So the probability of a coincidence will be the square of the amplitudes associated with these two processes. That's what we just said, our good friend, Professor Dr. Herr Richard Feynman. So what is this? Let's say this was a 50-50 symmetric beam splitter. So this is equal to t squared plus r squared. But t squared is a half, and r squared is
Yeah, that's all over two.
minus a half, which means this is 0. Which means I will see no coincidences in this guy. If this were two light beams on a beam splitter, some of the intensity would get reflected, some of it would be transmitted. I would always see some photocurrent on both of these detectors. I would never see this destructive interference. This is two-photon interference. And it blew everyone's mind. Now, it's interesting, I was a grad student, first year grad student when this experiment was done by Mandel, who's one of the greats of quantum optics. This is known as the Hong-Ou-Mandel interference. And it's, at the time, people didn't really appreciate how important this was. Really, there was a very technical reason they were doing this. But what they measured this as a function of the displacement of this, and what they found on this coincidence count, what they saw as a function of that delta L, the coincidence counts they saw looked like this. So when this path, well not this, let's say this path, delta L, is changed a little bit, that when I'm exactly aligned and I can't tell, then I get 0. The reason is that these are wave packets. And if the two wave packets don't overlap, then I know which one it is because they're distinguishable. One is early. They wanted to know what was the width of the wave packet that was created in this particular spontaneous parametric conversion. But the two-photon interference was like the thing. Yeah,
That's the famous dip, right?
I'm listening.
So you said that we wouldn't see two-photon interference usually. And
For
then-
classical light, if I took two laser beams and I put them on the beam splitter, I would see some of it here and some of it here.
Okay, and so then for that experiment, they had to make it coherent somehow?
This is a special process whereby this was a process by which they took an ultraviolet photon and it broke up into two IR photons in a kind of like a decay process. These two photons are correlated. There's a special quantum correlation between these two photons. We'll talk about this next semester. This is a process of spontaneous parametric conversion. And this is a two-photon correlation that doesn't exist classically. I would have, to make these guys indistinguishable. Yeah.
Yeah, I think I asked you something similar last class too. Now that's what bothers me a little bit in the experiment too. So when I just have one crystal, how important is the spontaneity of this process? What happens if I stimulate it?
Oh yeah, well it's a different story. If I were to have another beam here, an IR beam, this is called parametric amplification,
Yes.
right? And then I don't have this exact correlation. I have different kinds of correlations. But we're way ahead. We can talk off.
Sure.
It's a different process. The nature of the quantum state is quite different than the spontaneous is important to see this Hong-Ou-Mandel. Yeah.
I don't understand why you call the one photon classical interference, because the effect still comes from adding probability.
Yeah, you're right, Spencer. It's a little bit, it is a quantum effect. It's not classical, but I'm saying that the interference we see from the quantum wave, it had to be, of course, everything is quantum, right? Everything is quantum. What we observe in the world is fundamentally from quantum mechanics. But I'm saying that this is effect is sort of like classical interference because the way in which the interference effects that we see are the same effects that we see for the classical waves. That is to say, this interference pattern is the same exact pattern as the probability amplitudes. They're one and the same. Should I call that classical interference? You know, yeah. Yes, sir.
So when I took the sum of the amplitudes, I get 0, I can just think of that as like completely deconstructed.
It's complete destructive interference, which means the photons always go off together. They always do this or this, but they never do this. Yeah.
In this process where we're creating these two indistinguishable photons, if I were to like turn the dial on that and sort of make it happen, you know, very, very rapidly to the point where like it's almost like just a beam of photons. In what regard, like when does that stop being quantum and start being classical, and then we stop seeing this effect? Like I'm trying to turn the knob, and I'm wondering, like.
I mean, you know, if the spontaneous process happened more and more and more, I could have another pair be created sort of soon after this one, right? And if I didn't gate them fast enough, then I might not see this interference anymore because it's coming from two photons that are not correlated with one another.
I see.
Okay, so, but if I gated it properly, it would still be quantum.
I see.
Yeah.
So, can I think of it, because experimentally, like, I have like a little piezo that's tuning that beam, or that mirror, excuse me.
Yeah.
Is that what sort of, can I think of that as what controls the visibility?
Yeah,
Whether or
so
not
the whatever I'm doing, you know, piezo or whatever to move this around will move these two photons. If they're not overlapping with one another, they become distinguishable. It's only when, because I know it's that one, because one came a little bit later than the other. So the information encoded in its time of birth, right? But if they're born at exactly the same time, and I don't delay one twin relative to the other, they are twins, and they're really identical. There is nothing that tells them apart. Then I'll see this interference.
So, you're saying that, for example, in these two cases, the middle ones,
Yes.
you cannot tell them apart, right? Because they click the same, you click at the same.
These two, well, these are just this. I mean, I'm saying these two guys are in. If I see a click here and a click at here at the same time, I don't know whether it happened because both photons were transmitted or both photons are reflected.
Yeah, but the same thing happens here, you don't know which
There's
one.
only one process that leads to both of these guys going click. There's no other process. So there's no interference here. So what will happen if I perfectly align this two-photon interferometer is that half of the time both of the photons go here, and half of the time both of the photons go here. 50-50, I don't know which ones. But I will never get one click here and one click here at the same time, because those two processes destructively interfere. It's a two-photon effect. Yes, sir.
The length scale of the wave function, does it have anything to do with the wavelength?
Yeah, that's a whole other, I mean, it's really a question. We digress. We'll come back to those details. This is a preview of things to come. But we'd have to think pretty carefully about the whole nonlinear process and why it's broadband, why there are very narrow wave packets. It's a longer story, and we'll never get anywhere. So we gotta keep moving. Yeah. All right, good, excellent. So, so what I just to sort of make this a little bit more generic now, not just about light and the wave function of the photon, but just quantum mechanics more generally, right? So we can think about this notion of quantum coherence. Superposition. Okay. So generally, we know in quantum mechanics, we think about Hilbert space. And we think about the state of the system as some vector in Hilbert space. Okay? In quantum mechanics, all we can do is predict the probability of a measurement outcome. That's all we can do. That's all quantum mechanics provides for us. It tells us how do you predict the probability of measurement outcomes. Okay? So we have measurement outcomes. I might label them with some index, alpha, okay? And there's some probability of a measurement outcome, and the probability of the measurement outcome is equal to some square of some amplitude. I'll call it C alpha squared. This is my probability amplitude associated with that outcome. Now, how do I find that probability amplitude C? Well, it depends on what that outcome corresponds to, okay? That outcome is related to whatever measurement I'm doing. So typically we think what most people learn when they learn about quantum mechanics, we talk about measuring observables. I'll come back to this later. It's a little bit too constraining to think about a measurement in this way, but I'll just start that way. And an observable we think about as having a Hermitian operator well, let me call these outcomes little a. Capital A. And the outcomes are the eigenvalues of A. So A has eigenvectors and eigenvalues because it's Hermitian operator, and each one of the outcomes is one of the eigenvalues of the Hermitian operator. And the probability amplitude we get by the inner product. Okay? So that's the probability amplitude. Right? So let's, and this is the Born rule. So let's, of course, what I just said, quantum coherence comes from superposition. So let's say that psi itself is a superposition of two states. Okay. and I want to know what's the probability of finding outcome A. That's like, what's the probability of finding the outcome that the detector goes click and output poor? That's an outcome. It's something that happens. What's the probability of that? Well, we just said it's this squared. So that's equal to C1, C2, side 2 squared. Everyone with me? Because I take the inner product with A, which is, it's a linear thing, and then I square it, right? And this equals C1 squared so C2 squared. Well, let me write this on the next board. So the probability of seeing that outcome is, I'll write it this way. Right? So I write this out explicitly again to emphasize the difference between quantum logic and classical logic. What is this? This is the probability of seeing outcome A given that I was in side 1, and this is the probability of being in 1. Okay, assuming these two are orthogonal, let's assume that. Let's just assume that to be true, okay? And this is the probability of seeing A given that it was in 2. And this is the probability that it was in state 2. That's classical logic. This isn't. This is quantum coherence.
So what makes difference classical and quantum is interference, right?
Is it? That's it. And we see that the interference here depends on these coefficients. It's not C1 squared or C2 squared. It's something about the relationship in C1 and C2, which depends on the relative phase of these guys, right? So the phase difference, if I write each one of these guys as a complex number with a magnitude and a phase, the phase difference, the relative phase matters in the same way that the relative phase of the classical waves matter. And so quantum coherence is all about the control of the relative phase between those amplitudes, okay? So maybe in the last 5 minutes I want to say, well, okay, so what does it mean to not have coherence? I mean, we just said, yeah, look, we got superposition, we got coherence. The same thing was here. If we come to this interferometer, back over here, we see this nice interference fringes. And in fact, what we would say, this pattern goes on forever, according to this. Oh, God, I can't draw. With perfect visibility, that is to say, the bright point and the dark point it's maximum visibility. This would have infinite coherence length. That don't exist in the real world. So why not? Well, because when we think about, say, the classical waves aren't perfectly coherent. Why not? We just said if we had a monochromatic field, it would be perfectly coherent. But there ain't no such thing. And because the sources that we have of the waves are not perfectly coherent, which is to say, let's just think about classical sources of light. For example, this light bulb or the sun. What's happening is, we can think about it classically, is that, well, I can think about the light coming from electromagnetic radiation. We remember electromagnetic radiation. How does electromagnetic radiation happen? It's because charges are oscillating and they're accelerating. So I can think about, a charge on a spring, like an electron. I can think about the Lorentz oscillator model, where I think about the electron bound to the nucleus, and it's oscillating up and down and radiating a dipole pattern of electromagnetic waves. But really, this would have a well-defined, if it was just oscillating, would have a well-defined phase. But in fact, what I really have is a collection of all these oscillators. And I don't know the phase of one relative to the other, because it's undergoing all kinds of stuff. There's collisions, who knows what's going on in the solid state material. There's all kinds of collisions, all kinds of stuff happening, and the phase is random. I don't know what the phase is. The amplitude might be random. It's random because I just don't have the information. If I knew it, I would be able to predict what all these things are. So when we talk about classical course of light, we talk about what we call statistical optics, which treats the complex amplitude as a random variable, but a classical random variable. Okay? Meaning I don't know what it is, okay? But I might have a statistical model for what that amplitude is. And what that means is that when I look at the intensity, really what I have to think about is integrating over, I think about it, some integral over the field, whatever that means. We have to think of it's a more, integrating over functions is kind of complicated, but let me just ignore that for a moment. I have some probability distribution of the electric fields, and then the squares of the amplitudes. That's what I really should do, because I don't know what the electric field is. I have to average over some probability distribution. And when I have this in a superposition of, say, two fields, say A and B, where this depends, for example, on the relative phase between A and B, what we can see in this situation is if I have my probability distribution has a kind of random phase, I don't know what the phase is because of collisions that are happening, then this is generally going to wash out this interference when I average over the distribution of possible phase differences, and I don't know which one it is. And so what that will mean in this situation is that I will typically get interference fringes that look like this. With ultimately no interference and half of the amplitude coming out one port and half of it coming the other. I can only see that interference when I have the difference between the paths sufficiently short that I haven't lost that phase coherence. But here, the lack of coherence is coming from the lack of complete information about what the oscillator is. If I knew it, I might be able to reconstruct it, but I don't, okay? So there's missing information. And so we wanted, our next step is to generalize this to this problem. Here, we saw quantum coherence because we knew what the wave function was. We knew what the state of the system was. Someone did a good job and they prepared the state psi. That particular psi happened to be superposition of psi 1, psi 2. But if I didn't know, if somehow the experimenter didn't do a great job and you didn't prepare, you didn't know exactly what state it was in, I would have to somehow statistically average this. And there lies in the rub. What we will see is that there is this craziness mixture between the classical statistical lack of information and the other part, things are random in quantum mechanics, even when I have 100% of the information I could possibly have. They're still random. But what part of that randomness is due to the fact that I didn't know the preparation exactly and someone didn't tell me it, versus what part of the randomness is coming from the fact that things are random in quantum mechanics? That's where things get interesting. Yeah.
When I look at it, it looks like as I sort of increase delta L, my interference pattern almost becomes like dampened.
That's right.
I think of that almost as my system becoming more and more almost like open, so to speak. I know less and less information.
I think the bottom line that is to emphasize here is the visibility of these fringes, the difference between the high point and the low point, depended on there being good interference. As the interference goes away, it's as if it was a half of the intensity goes one way and half the intensity goes the other way. The fact that there's more intensity at one output port versus the other was because of interference. But if the interference is washed out in some way, if I lose coherence, well, that's kind of like a damping. It is a kind of damping if I wanted to think about it. The source of that statistical optics is a kind of damping, right? I mean, it's because I'm missing information. Yes, Omar. And then we gotta get out of here in 1 minute.
So imagine I know everything certainly.
Yeah.
Even in this picture, if I get delta L, my delta is large enough so that my wave packets don't overlap anymore. I would still get similar.
Right. So that is an interesting point. There's not a big difference, as we will see. This kind of interferometer only depends on the spectrum of the light. So I could have two different things. I can have a mode-locked laser that is perfectly coherent, that puts out pulses, that is very broadband, but it's coherent in a certain sense. It would still show this damping, because if the pulses don't overlap, I don't see it, versus this kind of light, which is also broadband but incoherent. In a one-photon interference experiment, I can't see the difference. But you have the premonition when we talk about higher order coherence, will tell the difference between them. because it's really photon by photon. In this case, it doesn't make a difference. But we'll pick this up next time.
Can we use a micro resonator instead? It'd be cooler than an old block laser.